The motor provides for the simulation in your classroom the turning power for the shaft that is connected to the simulated antenna. The shaft would be connected between the motor and the antenna base. It is not connected at this moment. For this simulation, this is the positioner of the antenna. It is a rheostat, and you would simulate the antenna motion by changing the screw to turn the rheostat. Your entire operation depends on this power supply, which provides the high voltage and the low voltage needed. There are red wires and black wires attached to the back of the power supply. In addition to the red and black wires, you will see a white wire and a green wire. In this case, the green wire has been attached to establish a ground for the motor, and if you look really close, you'll see a black wire sliding in behind the white wire. This wire that is moving up and down, the whole thing is the wire that's coming from your plug in the wall. One set of red wires goes to the box that provides signals from the Arduino. It is the final control element. The black rods that you see are the heat conductors to keep the circuit cool. The green boxes in the front are how the signals are distributed. The black and red pair and on the left returns to the electric motor. The actual computer controller in this simulation is an Arduino. It happens to be the Uno. Any Arduino will work. It has the signals coming in from the outside world and changes those signals to go to reposition the antenna. The breadboard simulates a circuit that is often needed to connect the sensor, which is on the left, to the controller, the Uno, which is on the right. In this white breadboard, there are 2 capacitors and 2 resistors.
Now that you've seen the components required to build this demo, let's talk about how it works. This hand-adjustable rheostat is used to mimic the adjustments that would be made in a real-life example. In the image shown, if the wind disturbance is detected, the antenna azimuthal angle detector will be triggered to readjust the gear to reposition the antenna back to a certain set point. This rheostat here in this demo is used to simulate that motion. The dots represent the 8 data points that are collected when there is no wind disturbance. Here you can see the set point is set to 9 volts with a 0.0 volt antenna rotation disturbance signal. When the rheostat is turned clockwise, simulating a wind disturbance, you can see the wind disturbance of 2.8 volts disturbance signal moving the antenna signal down to 6.2 volts as represented in this diagram. Now see the 8 data points collected that is used to illustrate a proportional model curve that is attempting to bring the antenna back to its set position. You can see the wind disturbance starting at the 60-second mark in this model of 7 data measurements. In order to show the proportional control, we focus on the CT output value. This model takes into account 2 of the 4 values represented in the C0 output and the KP value. This model and equation is used to adjust to the wind disturbance and return the antenna to the set point position, factoring in a 2.8 volt antenna rotation disturbance signal using 6 model control signals. The blue curve represents the proportional control model while also illustrating that the offset never becomes 0 volt. Here notice the KP value is 0.4, with a KI value of 0.0 volt seconds and a KD value of 0.0 volts per second. With this model, the antenna will readjust back to the set point. Now we reset the rheostat and return it to the set point position to 9 volts with the 0 volt offset. This model indicates the wind is not blowing. In this model, this simulates the wind blowing in the opposite direction. Now we are simulating a 1.5 volt antenna rotation disturbance signal in the opposite direction at the 60-second time mark. This is simulated by the rheostat rotating counterclockwise and represented by the red arrow pointing up. Similar to the example previously, the blue curve illustrates the correct pathway to adjust for the wind disturbance. Here, notice the Kp value is 0.4, with the Ki value of 0.0 volt seconds, and the Kd value of 0.0 volts per second. With this model, the antenna will readjust back to the set point. As you can see now that the counterclockwise motion returned the rheostat to the set point position. Now, let's see what it looks like. In this demo, it's critical to ensure you do a full pre-check of the system and ensure power is on and ground before conducting the demo. You will see the models represented in a real-time display in the bottom right-hand corner. You can see that the curves move up and down as the rheostat is turned in a clockwise or counterclockwise motions. This signifies your demo is working by seeing the curves change as your rheostat rotates in either direction. Thank you for learning with us today. For more information, please visit flate.org or contact us at the email displayed below.